Hey there, this is the lecture video for Chapter 5, Section 4. This one is a big one, so just prepare yourself for that. Get comfy, get a snack, whatever you have to do to dig in. We're going to be using some old formulas, so if you've been doing what I suggested way back and keeping separate notes for notation, now is the time to bust them out. They are the formulas for population mean, variance, and standard deviation. You'll also need to use your calculator for this section, for some easy stuff, and for some functions we've used recently. There's a lot of detail to follow this time, and it may feel like a lot of work for not much reward by the time we get to the end of a problem. But if you ever use this in your work life in the future, you're going to need to know how to do this and what these different terms and formulas mean. So it's worth the effort to learn them now. Unfortunately, some of the formulas are going to require a bunch of little detailed work, and that can be a pain, but a lot of the work is done for you on the lecture notes. So just follow along, do your best to stay on top of what is required. If you need to pause the video, do so. If you need to put a star next to something so you can ask in class, do that too. Okay, you can do this. Let's dive in. Welcome to the lecture video for Chapter 5, Section 4, Sample Distributions and the Central Limit Theorem. Our objectives are to learn how to find sampling distributions and verify their properties. We're going to learn how to interpret the Central Limit Theorem, and then how to apply that theorem to find the probability of a sample mean. So to begin with, the probability distribution of a sample statistic is called a sampling distribution. It's basically formed when samples of size n are repeatedly taken from a population. In this section, we're going to focus mainly on sampling distributions of sample means. For example, let's say WVUP is our population, and we wish to know maybe the average number of televisions per household. Mu and sigma are unknown. Population parameters are unknown numerical characteristics of the population. Now again, the mu describes the true average or the true mean, and sigma describes the true standard deviation. These are unknown because we're not able to ask every single person at WVUP. Maybe we try to take multiple samples of the same size. So within each sample, we're going to calculate an average. Within the first sample, I've got x bar sub 1. Then I take another sample and I have its mean as x bar sub 2, and so on. Now all of these values become my data points, my sampling distribution of sample means. Sampling distributions of sample means have two very important properties. The first states that the mean of the sampling means, mu sub x bar, is equal to the population mean mu. This number, mu sub x bar, is the average of the averages, the mean of the means from all my little sample groups, and it happens to equal the average or mean of the original data set. The second property is an oddly specific equality. It states that the sigma sub x bar, or the standard deviation of the sample means, is equal to the population standard deviation divided by the square root of the sample size. This value, this ratio, remember that just means a number divided by another number, has a special name. It's called the standard error of the mean. Okay, let's try an example to show how these properties are true. Population values 1, 3, 5, and 7 are written on slips of paper and put in a box. 2 slips of paper are randomly selected with replacement. Find the mean, variance, and standard deviation of the population. Remember how I warned you that you'd need some old formulas? Here's where they come in. We're going to refer to the old formulas we had for the population mean, variance, and standard deviation, and we're going to adjust them slightly to use for the sample distributions. But before we adjust them, because we want to show that these properties hold true, we're going to first find the values for the population and then compare. So we need the population formula. I've provided them here, but it doesn't hurt to refamiliarize yourself with your copies because you'll need them and want to get reacquainted with how they work. Pause the video if you need a moment to find them or jot these down. At this point, though, I'm going to take you on a little bit of a side trip and let you in on a little secret. You can recall any of the variables that you've already performed a function on in your calculator. What do I mean by that? Well, let's look at a function that we used a bunch at the beginning, the one variable stats command. First, we need some data to work with. We'll use the numbers that we'll need for the problem I just introduced. So how do we do that? Do you remember how to enter numbers into the calculator? The numbers we need are 1 through 7 inclusive. Pause the video for a moment and test yourself. It's okay if you couldn't quite remember. You want to press Stat, then Enter, then type in each number pressing Enter between the numbers. That will put them into the L1 list. When you're done, let's revisit our old friend one variable statistics. Here's how you enter that. Press the Stat button, then arrow over to Calc. Then while it has one variable statistics selected, press Enter. Then make sure it has L1 selected, or you may have to tell it L1 by pressing the second key, then number 1. Then press Enter as many times as needed to calculate. It should give us a list with several variables on it with values next to them. Yours may be slightly different, but they should be very similar to what you see on the screen. Let's briefly go over them. The first one is X bar. You may not be able to see it on this screen very well, but that is an X with a bar over the top of it. We've dealt with this for a while now. That means the sample mean. The next one is the sum of all the elements. The next is the sum of all the squares, or sum of squares, or SS sub x. The next is the sample standard deviation, or just S. The next one is very important because it's the reason I'm bringing all of this up. Sigma x is the population standard deviation, or just sigma. N is the number of elements. Min x is self-explanatory. Q1 is the first quartile. Med is the median. Q3 is the third quartile, and max x is the maximum. These are the variables, and once you perform that command, you input those values into the variables as values that can be recalled until you replace them by performing another command with that variable. Okay, let's go back to that population standard deviation. One value our calculator doesn't give us in this list, or in any of the functions we've used yet, is variance. But we know something about variance. It's the square of the standard deviation, right? Let's go back a few slides to those formulas. Yes, see, variance is the square of standard deviation. Usually we perform the operation by finding the variance first, then finding the square root of that to get to the standard deviation. Well, if we can easily find the standard deviation, and it'll be more trouble to find the variance, why not go the other way around and find the standard deviation first, then square it to find the variance? So back to where we were. Here's an option if you want to use it. If you would like to do this, follow along, and you will be using the numbers that we worked with a moment ago, 1 through 7. First, enter your data into your calculator into L1. Then perform the one variable stats command on it. Now, to recall the standard deviation variable, press the vars button, then select or press 5 statistics option, then press 4 or arrow down to select the 4 option, which has the standard deviation variable on it. Notice at this point on your calculator that you could recall lots of different variables if you chose to. Then you see your variable on the main screen. Now you tell it what you want to do with that value. Since we need to square it, you press the X square button, then press Enter. It should give you the value that you want. So note that for yourself, that the variance is whatever you came up with, because now we're going to work the problem that data came from. Be sure to put this in your calculator notes if you want to use this hint in the future. This is recalling variables, and it's after you've already performed some kind of function or command on those variables. Pause the video if you need to. Okay, let's move forward. Back to our problem. So we have these problems from a while back, mean, variance, and standard deviation. We just talked about how we can easily get these values from our calculator, or you can find them manually. Either way works. You may be wondering why we did the command with different numbers than are shown here. That's because there's more to this problem than just this beginning part. Make sure you have written down what you found for variance with the previous numbers if you decide to use that shortcut with these numbers now. Because if you'll remember, the calculator writes over the value when you run the command again. So the mean is the sum of the values divided by the total number of values. The variance is a little more complicated, but now you know an easier way to find that. Or if you want to do it by hand, remember you find the individual deviations or differences between the values and the mean, square them, then add those squares together and divide by the total number of values. The standard deviation is then the square root of that number for the population. So we have our population, mean, variance, and standard deviation. If we were to graph this, the probability is what drives what this would look like. Because there is replacement, there's an equal chance that any of the slips of paper are chosen, so the distribution is uniform. The probability for each value of x in the population is 0.25 or 1/4. Now to create our samples from this very tiny population. We draw 2 slips of paper randomly with replacement in between draws. The list of all possible samples of size 2 are given in this table. Here are all the possibilities for selecting the first piece of paper. Here are all the possibilities for selecting the second piece of paper. Because we're putting them back after drawing them, because it said with replacement, there's a possibility of drawing the numbers twice. So we do want to include the possibilities of doubles as shown. So we could have 2 1s, 3s, 5s, or 7s. Remember, this is saying that we drew the first number first, replaced it, then happened to draw it again when we drew the second time. The second column is the mean of each of these tiny samples of size 2. So the average of 1 and 1 is 1. The average of 1 and 3 is 2, and so on. And when we figure all of these out, we find that the means form the sampling distribution of sample means. So what are all the possible values of x bar, or the sample mean? X bar could be 1, 2, 3, 4, 5, 6, or 7. That's where we get that list of numbers we were working with on the calculator before. There are more than one instances of these possibilities, but the set of possible values for x bar are these values. Now we just create the sampling distribution like we did before, but for the sample means. Here's what that would look like. These are the possible values that the average from the samples could take on that we just found. Now remember, these are means. These are the values of the means. If we count up how many times each of them occurs, we will get the frequency of each, and that would allow us to get probability. First by totaling the frequencies, and then by dividing each one by the frequency total. So we would divide this first number, 1, by 16, then the second 2 by 16, and so on. That would give us probabilities first in fraction form, then in decimal form. So the mean of the sample means of 1 happened once, so we have one occurrence, and we divide that by 16, and we get 0.0625. The second occurrence happened twice, so we divide 2 by 16 and get 0.1250, and so on. That helps me create the probability histogram of the sampling distribution. Notice the shape of this graph is symmetric and bell-shaped, and that it approximates a normal distribution. That's a really important property to keep in mind later on when we're talking about the Central Limit Theorem. We're partway there now, but the next step is to prove that these two properties we outlined earlier are true. To do that, we now have to calculate the mean, variance, and standard deviation of the sample means, which means we have to adjust the formulas to fit our content because we're dealing with samples instead of population, and we're dealing with means instead of original data. So for the mean, the difference is that the numerator will be the sum of all the means, or x bars, multiplied by the frequencies, and the denominator will be the sum of all the frequencies instead of the population total, or n. To show that the properties are true at this point, you need to verify that the mean, or mu sub x bar, is equal to mu for the population. The variance adds one more step. After the deviations have been squared, you'd need to multiply each one by the frequency, then add them together and divide the whole thing by n, which is very similar to what we did for frequency distributions. The standard deviation is still the square root of the variance, but in order to prove that the properties hold true, you need to do an additional comparison. The property states that the standard deviation, or sigma sub x bar, must be equal to the population sigma divided by the square root of lowercase n, or the sample size. Okay, let's see if that's true for this one. To do this, we need to work out some problems. The first one, we multiply each x bar, or mean, by the frequency that x took on that value and add them up. The first one is the mean, 1, times the frequency, 1. Then the second is mean, 2, times the frequency, 2, and so on. And those are added together, then divided by the sum of the frequencies, which was 16. For this, we get 4. Since this is what we found for the population mean, we have satisfied this property and found that mean of the sample means is equal to the population mean. Next, we find the variance of the sample means. This is a little trickier to follow, but if you look at each part individually, you can track it. The first part is the first x bar, 1, minus the mean, 4. The difference is squared, and is multiplied by the frequency 1. Then, this is added to the next x bar, 2, minus the mean, 4. Then the difference is squared, and multiplied by the frequency 2. And so on. And that is done for all of the numbers, all of the x values, and the whole thing is divided by the total of the frequencies, 16. We end up with 40 over 16, or 5/2, which is 2.5. If we take the square root of that for the standard deviation, we get about 1.6. Now we need to look at satisfying the second property. We satisfied the first property, which said the mean of the sampling means is equal to the population means. But the second part says that the standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size n. So let's look at that. Our sample mean standard deviation was about 1.6, and our population standard deviation was square root of 5, and our sample size was 2. So we put that all together, and we have square root of 5 over square root of 2 is about 1.6. So yes, the sample mean standard deviation is equal to the population standard deviation divided by the square root of the sample size. Good job. So yay us for doing math, but why do we need to know this? What purpose does it serve? Well, if we know the population mean, then we already know the mean of the sampling distribution of the sample means. And knowing the population's standard deviation and the sample size gives us the standard deviation of the sampling distribution of sample means. Long story short, it will help us take shortcuts in the future. And we're about to learn a theorem where this bit of knowledge will come in handy. So let's talk about that theorem. It's called the Central Limit Theorem, and it comes in 2 parts. The first part says, if samples of size 30 or greater are drawn from any population with mean mu and the standard deviation sigma, then the sampling distribution of sample means approximates the normal distribution. And obviously, the greater the sample size, the better the approximation is. The second part of the Central Limit Theorem says that if the population itself is normally distributed, then the sampling distribution of sample means is normally distributed as well for any sample size n. So in either case, the sampling distribution of sample means has a mean that's equal to the population mean, and it has a variance equal to 1/n times the variance of the population. Thus, the standard deviation is equal to the population standard deviation divided by the square root of n. This value is called the standard error of the mean. If you look at the equation, it makes sense, right? Our work with variances and the standard deviations has shown us that their relationship is usually from square to square root or vice versa. Well, that's the same here. They've just introduced a fraction with the sample size. This theorem is very important, so make sure you're recording this in the notation area of your notes. It's basically telling you in part 1 that no matter what the shape of the population distribution, you know that this function, when you take a sample greater than or equal to 30, you're guaranteed to have a sample distribution that is normally distributed. In part 2, it tells you that if we already know that the population has a normal distribution, then we can take samples of any size n and still end up with a sampling distribution of sample means that's normally distributed. So why is that helpful to us? Because identifying a distribution as a normal curve puts us in z-score territory, which makes things so much easier to handle. Let's do some examples. A study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.9 hours, with a standard deviation of 1.5 hours. Random samples of 100 sleep times are drawn from this population, and the mean of each sample is determined. Find the mean and the standard deviation of the sampling distribution of sample means. Then sketch a graph of the sampling distribution. So first of all, don't let the shape of this distribution scare you. We know we're working with the central limit theorem, so we're likely going to be working with a normal distribution. But let's check the conditions. Part 1, are we drawing a sufficiently large sample size? Yes, 100 sample sleep times. That is greater or equal to 30. Now we know that the sampling distribution of the sample means will be approximately normal, and it also tells us that the mean of that sampling distribution is going to be equal to the population mean, and that the standard error of the mean, sigma sub x bar, is going to be equal to sigma divided by the square root of n. So they gave us the population mean, so because of the theorem, we know the sampling mean to be 6.9 also. For the standard error of the mean, we just plug into the formula the population standard deviation, which was 1.5, and the square root of the sample size, which was 100. We get 0.15 as our sample standard deviation. Here's what the graph would look like. Notice the variation is very narrow because the standard deviation is only 0.15. Let's do another one. The training heart rates of all 20-year-old athletes are normally distributed, with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution. Then sketch a graph of the sampling distribution of sample means. First, let's check for our conditions. The sample size is only 4, so you might think we can't apply the central limit theorem, but it states that the population data are normally distributed. So according to the second property of the theorem, we can apply the rest of the theorem, which means that the sampling mean will be the same as the population mean of 135, and the sample standard deviation will be equal to the population standard deviation divided by the square root of the sample size. Pause the video and do these calculations. Hopefully this is what you came up with. The mean is 135 beats per minute, and the standard deviation is 9 beats per minute. And this is what your graph would look like. So we talked about how this theorem would make our lives easier because we could use z-scores to make it so we're working with a standard normal distribution. Well, here's where that comes in, but I need to caution you about something with these formulas. You need to be very careful that you remember the context in which you're using this formula. This standard formula is the x value minus the mean over the standard error, which normally reads x minus mu over sigma. But when you're dealing with the sample mean distributions, you need to remember two things. One, you're dealing with averages. So instead of x's, you're dealing with x bars. And two, instead of sigmas in your denominator, you're dealing with a ratio of the population standard deviation divided by the square root of the sample size. It's important to keep those straight. If you need to write some extra notes for yourself in your notation area, pause the video and do that. Help yourself keep these straight come test time. Alright, let's do some examples. The figure shows the mean distances traveled by drivers each day. You randomly select 50 drivers ages 16 to 19. What is the probability that the mean distance traveled each day is between 19.4 and 22.5 miles? Assume the population standard deviation equals 6.5 miles. Well, the central limit theorem tells us that because our sample size is greater than or equal to 30, which it is, it's 50, the sample distribution of sample means is approximately normal, and the sampling distribution of sample means is going to be approximately normal with a mean mu sub x bar equal to the population mean. Well, our population mean is given to us in the picture for the age range 16 to 19 as 20.7 miles. So the sample mean is 20.7. We also know that the standard error of the mean sigma sub x bar is going to be equal to sigma divided by the square root of n. Well, sigma is 6.5 and our sample size is 50. So divide 6.5 by the square root of 50 and get about 0.9 miles, which is our sample standard deviation. Now that we have these values, we can work on standardizing this graph. First, we need to find the z-scores for these values using the information we just calculated. Z-scores correspond to the sample means of 19.4 and 22.5. We know that our mean is 20.7 and our standard deviation is the ratio of 6.5 divided by square root of 50. We find that the first one has a z-score of about negative 1.41 and the second has a z-score of about 1.96. So what do we do with this information? Well, we want to find the probability that someone would drive a distance within this interval between these 2 points on the graph. We've done this in the past by using different formulas with z-scores. This time, we're wanting to find the area between two z-scores. So this is handled by finding the difference between them and using the normal CDF function on your calculator. Pause the video and find your notes for that function and do that calculation now, using negative 1.41 as your lower bound and 1.96 as your upper bound. In case you've forgotten how to do that function, you press the second key, then bars, then arrow to normal CDF, then put in your lower, which was negative 1.41, then your upper, which was 1.96, then make sure mu is 0 and sigma is 1, and then press enter as many times as needed to calculate. You may need to put commas in and close parentheses depending on your calculator. And you should have gotten about 0.8957, which represents both the area between 2 points and the probability of something happening within that interval. In this case, the probability is 0.857 or 89.57%. Of all the samples of 50 drivers ages 16 to 19, about 90% will drive a mean distance each day between 19.4 and 22.5 miles. This implies that about 10% of this type of sample will lie outside the given interval. Okay, let's do a different type of question. Some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed with a mean of $21.72 and a standard deviation of $740. What is the probability that a randomly selected college student who uses a credit card to pay for school-related expenses paid less than $1,900? Number 2, you randomly select 25 college students who use credit cards to pay for school-related expenses. What is the probability that their mean amount paid is less than $1,900? And then compare the probabilities from parts 1 and 2. Okay, so number 1 is actually a problem like what we've seen in the past, because the purpose is to compare it to the questions from this section. So let's consider it. We have one question and we want to see the probability that they paid less than some number. Sounds like a z-score problem to me. So let's set it up to find a standard score. We have all the components we need. The x value is 1900, the mu is 2172, and the standard deviation is 740. So pause the video and find that z-score. So hopefully you got negative 0.37. If you didn't, make sure you put the subtraction in the correct order. Remember, you're subtracting the mean from the x value. So what do we do with this information? We want to know the probability that they paid less than $1,900. So we can use one of our handy-dandy functions on the calculator to figure this one out. Use the normal CDF function again. This time you're wanting the values less than a number. So you want your lower bound to be a very large negative number and your upper bound to be the number in question. You should have this trick in your notes too. See how this stuff pops back up? If you'd like to pause to try this on your own, do that now. So I'll go ahead and go through the instructions for those that don't remember. So do the second button, then bars, then arrow down to normal CDF and hit enter. Then do a large negative number. I type negative, then 1, then the second button, then the comma button. Remember, it has the 2 little e's above it that you use for scientific notation. Then 99, then enter, or you may have to use commas if your calculator does it that way. Then negative 0.37 as your upper limit. Then enter as many times as you need to calculate, or you may have to close parentheses and then enter. and you should get about 0.3557. Good work. The second part of the problem asks, if we selected a sample of 25 students, what is the probability that their mean amount paid is less than $1,900? Now I know what you're thinking, there's only 25 students. Doesn't that mean we can't use the theorem? Well, remember part 2 of the theorem says that if the population is normally distributed, we can assume that the sample mean distribution will also be normally distributed. So we can apply the rest of those properties. So we proceed similarly to the last one, except we're being very careful because we're dealing with means here. We need to think about the context and what values we're putting in for what variable. Because this is samples means, we need to put in x bar, and the denominator for our z-score formula needs to be population standard deviation over square root of sample size n. When we plug those amounts in, we get negative 1.84. Now we put this into the calculator similarly to the last one, using the normal CDF formula, with a large negative number for the lower bound and negative 1.84 as the upper bound, and we get 0.0329. So what does this mean? Well, here are some possible interpretations. There is about a 36% chance that a college student who uses a credit card to pay for school-related expenses will pay less than $1,900. There's only a 3% chance that the mean amount a sample 25 college students will pay is less than $1,900. And because there is only a 3% chance that the mean amount a sample of 25 college students will pay is less than $1,900, this is an unusual event. Remember, anything less than 5% is unusual. All right, that was a big lesson. You did great hanging in there. Make sure you got all the calculator notes and notation. That formula is pretty important, so make sure you have it in a good place that you'll be able to reach it during test time. Only one more section to go for this chapter. Talk to you in the next video.